In today's video, we are going to attempt to answer what initially seems like a straightforward question. How accurate is RTK GPS? Let's start off by looking at the manufacturer's listed specifications and try to get a full understanding of what they actually mean. There seems to be a range of terms used when a manufacturer quotes the RTK accuracy or precision of their unit. EMLID uses position precision, Spectra uses real-time accuracy, Leica uses measurement performance and accuracy, and Trimble and Topcon both call it position performance. Right off the bat, you can see there is quite a bit of discrepancy in how each manufacturer is labeling the values they're quoting. Some are calling it accuracy, others precision, and some are sidestepping the decision altogether and calling it position performance. So, is this an accuracy spec or a precision spec? First, let's do a brief recap on accuracy versus precision. Accuracy can be defined as the degree of closeness of the value of a measurement to the true value of what you are attempting to measure. But since we can never know the absolute true value of anything we are trying to measure, we can instead use a value that is as close to error-free as possible. Typically, this is done by taking measurements using a system with an inherently higher accuracy than the one being tested. Precision, on the other hand, is the degree of closeness of measurements to their mean, or how well the measurements fit to each other. In other words, precision can be thought of as a description of random error. The issue with calculating precision and calling it accuracy is the measurements may contain a bias in the form of a systematic error that skews the mean away from the true value. If we are trying to measure the distance between A and B with an RTK GNSS receiver, we could easily determine the precision of a set of measurements as we only need to compare the measurements to each other. But to determine the accuracy of that distance measurement, we would need to know the true distance between A and B, or as close to it as possible. If the 2 points were intervisible and the proper equipment and procedures were used to eliminate systematic error and reduce random error to an acceptable level, and we could get a reliable set of measurements with a total station, that value would suffice in most cases to determine the accuracy of this particular distance measurement of the GNS receiver. I reached out to a few of the big manufacturers in hopes they could clear some things up for me. I spoke to technical departments, sales reps, and anyone else I could that worked with these companies, and not a single person could give me a definitive answer as to what these quoted values definitively meant. One company I spoke to said, and I quote, "The stated RTK specs are the unit's instrumental precision. It comes from internal algorithms of the GNSS chip with a 50% probability CEP. When I asked some follow-up questions, I got radio silence. CEP, or circular error probability, is defined as the radius of a circle centered on the mean value that contains 50% of the actual GPS measurements. So a receiver with a 10 mm CEP precision will be within 10 mm of the mean measurement 50% of the time." A marketing manager from a different company said, and I quote, "Their RTK accuracy is currently tested under the ISO 17123-8 standard." Again, when I had a few follow-up questions, I didn't hear back. The more I asked around about these manufacturers' numbers, the more I realized this wasn't a particularly welcome question. When I pull up ISO 17123-8, one of the first sentences in it states that this should be used to determine precision or repeatability, not accuracy. As we start looking at the ISO standard, it becomes fairly apparent, in my opinion, that this indeed does not test accuracy, as there is limited effort to determine a true or accepted coordinate for any of the observations. And trying to come up with a value for accuracy opens up a huge can of worms because of the endless number of variables that go into determining a position from the GPS observation. So the question then becomes, does precision, which we can measure fairly easily, give us an approximation of our accuracy? Yes and no. An argument can be made for both, but if your argument is yes, precision can be considered accuracy in this case, then some conditions need to be addressed. If the error in our RTK measurement is truly random and follows a normal distribution and there is no systematic error present, then the mean should theoretically give us a reliable indicator of the true value. Our RTK GNSS system is collecting, decoding, and processing satellite signals and corrections from a base station to determine a Cartesian XYZ vector from a known point, the base station, to an unknown point, the rover. For now, let's ignore the error in the determination of the base point as we will focus on the relative accuracy between receiver heads. But if we wanted a better representation of system accuracy, we would need to incorporate that as well. The same goes with the horizontal and vertical centering errors of the base and rover. We need to know if the error in the vector from the center of the base receiver to the center of the rover receiver is Gaussian, or follows a normal distribution. To put it simply, if the errors in the vector follow a normal distribution, we can assume that they are relatively free of systematic error and that the mean value should be the true value within the standard deviation at a given confidence interval. Testing has showed that errors over a long duration of observation do in fact display distributions that match Gaussian patterns to within a few percent for carrier phase differential measurements that we use in our RTK solution. Differential errors over a short time period produce a scatter plot dominated by multipath, which is fairly consistent over a few minutes, and hence the distribution is distinctly non-Gaussian. Let's take a look at some graphing I did of continuous single epoch measurements that I took at two separate rover points over 4 hours. These first three graphs show the probability density of each axis of measurement for point 20,000 over 4 hours of observation. As you can see, they do follow a normal distribution quite well. If you look at this graph here, I cut out a section of the same data set and graphed the probability distribution in the same manner, and it's fairly apparent that this smaller data set does not follow a normal distribution. The following graphs show the plotted northings, eastings, and elevations of both points over the full 4-hour duration. There is quite a bit of variance of each individual measurement, especially at the beginning of the observation, but as time goes on, the positions smooth out and more or less hover around the mean. So, what is causing the error in the first place? Well, GNS observations are affected by the following. Radio signals are emitted from the satellite and travel to the receiver. The receiver then determines the flight time of that signal and uses the equation distance equals velocity times time to calculate the distance the receiver is from each satellite it is receiving radio signals from. These radio signals can bounce off nearby objects such as buildings or trees, before reaching the receiver, causing an incorrect distance measurement from the satellite to the receiver. In fact, QZSS, the Japanese quasi-zenith satellite system, follows an orbit that keeps them near zenith above Japan and was designed this way in part to reduce multipath issues in built-up urban areas such as you would find in Tokyo. Geometric dilution of precision is influenced by the geometry of the satellites in the sky, PDOP, and the clock error of the satellite and receiver, TDOP. If the satellites you are receiving corrections from are bunched together, the trilateration of your position won't be as good compared if they were spread out. GDOP is calculated by the square root of PDOP squared plus TDOP squared, and PDOP is calculated by the square root of HDOP squared and VDOP squared. Satellites in a GNSS system have highly precise atomic clocks on board, and the receivers use that time information from the satellites to calculate their positions. Relatively speaking, the clocks on board GNSS receivers are not nearly as accurate. Any deviation in the satellite's clocks or the receiver clock can introduce errors in the position calculations. There are also a few other factors that influence accuracy that are receiver dependent, such as the number of channels, frequencies, and constellations a receiver can use. More is generally better. Higher quality receivers with better signal processing capabilities can increase accuracy as well. Atmospheric conditions. The Earth's ionosphere contains charged particles that can cause delays in the GNSS signals as they pass through, and unfortunately the ionosphere delay is always fluctuating depending on location, time of day, and solar activity among other factors. The delay is frequency dependent. This is one of the reasons we receive signals in varying frequencies such as L1, L2, and L5. The troposphere, or the lower portion of the Earth's atmosphere, also causes delays in GNSS signals. Again, this delay is not constant and is influenced by atmospheric pressure, temperature, and humidity. Water vapor is a significant contributor to tropospheric delay, and it can vary spatially and temporally. GNSS receivers do typically incorporate models to account for troposphere effects, but they are not fully eliminated. Your base station is calculating corrections based on its known and measured position and sending that data to the rover. Since that correction is based on the location of the base station, it will be less accurate the further the rover is from the base. This makes up most of the ppm part of the accuracy spec. GNSS satellites have inaccuracies or deviations in the predicted orbital positions compared to their actual positions in space, and these errors impact the accuracy of the GNSS-based positioning. This wasn't an all-inclusive list of the errors that affect GNSS measurements, but these are the sources of error that have some of the most significant impact. ISO 17123-8 sets out the methodology to test and calculate the standard deviation of a GNSS receiver. I won't go over it in detail, but feel free to pause the video if you'd like to try it out for yourself. The ISO standard sets out the typical standard deviation equations to use on each axis of the coordinates separately. Then to check the calculated values, you use the standard deviation for elevation directly and take the square root of the sum of the squared values for northing and easting to get the DRMS, or distance root mean squared in 2 dimensions. And you'll remember from my other videos that as surveyors, we don't typically use a single standard deviation of confidence, but opt for the 95% confidence. To convert these values from 1 to 2 standard deviations, we must multiply them by 2. For example, for a Leica GS18 that quotes 8 mm plus 1 ppm horizontal ISO 17123-8 value, it's basically saying that you can expect your measurements to land within plus or minus 16 millimeters plus 2 ppm within the mean at 95% confidence. And according to their spec sheet, the elevation will be about double that. The quoted specs and the ISO tests are under ideal conditions, out in the open with no overhead obstructions nearby in times of low atmospheric disturbance. I ran the full ISO test procedure on 4 separate points, 2 points that were out in the open and in ideal conditions, and 2 whose view of the sky was partially obstructed. I will admit I was quite surprised at the precision that was obtained from the ISO testing on the 2 points that were out in the open. You may recognize the study site if you watch my video, Improving Your Survey Control Least Squares Adjustment with StarNet. I chose to run these tests on this site as I have a very accurate least squares adjusted control network set up here. The benefit of this is it allowed me to run rounds of observations to these new rover points and bring that data into my control network adjustment to determine highly accurate values for them to get an idea of what I could expect in terms of accuracy from these RTK observations. In terms of precision for the 2 points out in the open, we had an average DRMS at 95% confidence of 33 thousandths of a foot or 10 millimeters horizontally, and vertically at 95% we had 48 thousandths of a foot or 15 millimeters. If we look at the following graphs that compare the average error in coordinates of the measurements to the value of the points we're holding as true from the redundant total station least squares adjustment grouped into observation duration, we can see a trend starting to emerge. The longer the observation, the smaller the error. There are a few outliers here and there, but if I had to guess, if I had increased my sample size significantly, I'm willing to bet the outliers would start to disappear. There is nothing really surprising about seeing longer observations reducing error, as it follows logic and mathematics that the mean of more measurements will be more precise and therefore more accurate. So, based on this data alone, would I feel comfortable with quoting 1 centimeter horizontal relative accuracy and 2 centimeter vertical relative accuracy on RTK observations, considering I want to be certain to 95%? I would if I took at least two 180-second observations separated by enough time for the geometry of the satellites to significantly change, say 3 to 4 hours as recommended per ISO testing, and the points were out in the open in ideal conditions and I was using a nearby base. I will also caveat that with the fact that I would want to use a service such as gnsplanning.com to make sure I wasn't observing during a DOP spike or during a time of atmospheric or solar disturbance. Based on these two tests alone, I did not see standard deviations at the 95% confidence that exceeded these values when using the entire data set. And given the 180-second observations were significantly better, that gives me more confidence that I would hit that spec. If I had to quote a more realistic absolute accuracy that included centering error at both the rover and base along with factoring in the uncertainty of the base station's coordinates, I would not be able to use those numbers as I would need to start doing some error propagation based on the best estimates of those values. What about in less than ideal conditions? We aren't always so lucky to have points that we want to survey wide out in the open. Our first test, the 2 points were out in the open and they had a clear view of the sky above 10 degrees up from the horizon for about 300 degrees around. There were a few trees to the west, but they only cut off the lower 20 degrees from the horizon. For the next test, I set points closer to the treed area so that 50 to 60% of the sky was obstructed. The first point, 70,000, was halfway underneath a gazebo, and the second point, 80,000, was underneath some oak trees with open sky directly above and to the east. For 70,000, I had a 2D RMS of 182 thousandths of a foot, and the 95% standard deviation of the elevation was 132 thousandths of a foot. For 80,000, I had a 2D RMS of 124 thousandths of a foot, and a 95% standard deviation for elevation of 177 thousandths of a foot. And when we graph the error of the measurements versus the total station values again, the trend of error going down with an increased observation duration isn't as obvious. Based on this data set, a longer observation wouldn't necessarily increase the confidence of the measurement. Even at 180-second observation duration, I was seeing vertical error as bad as 22 hundredths of a foot for 80,000 and 14 hundredths of a foot for 70,000. The horizontal error was over 15 hundredths of a foot for both. I expected fairly poor results from 70,000 considering where it was, but I was somewhat surprised by 80,000 considering about half of the sky was out in the open. Even if I took two 180-second observations separated by 3 to 4 hours, in either of these situations, I would not feel comfortable quoting accuracy in either axis under a tenth of a foot. I would start by doubling those values before regaining any real comfort level. I chose to run this test as I see situations quite frequently of surveyors setting or tying property corners with RTK in conditions worse than these. It is important to know what you can and, more importantly, cannot expect in terms of accuracy when taking RTK observations in poor conditions. I get that there are time constraints to meet project budgets, but it's important to understand when a baseline, such as a lot line for example, will be able to absorb that kind of error. In order to get an error ratio of 1 to 10,000 for example at 95% confidence, between 70,000 and 80,000, they would need to be 2,500 feet apart. Up to now, all of these tests have been run from a nearby base, effectively eliminating any effect of PPM. I wanted to redo this testing using a distant base station. I connected to a core station through the Florida Permanent Reference Network that was 16 miles away, taking observations to the unobstructed points 20,000 and 40,000 using the exact same ISO testing methodology. When we look at precision of the measurements, we see almost exactly double the values we saw compared to the nearby base. These numbers are starting to creep up and remove a few use cases of RTK via an internet connection to a distant base station. This wasn't a huge surprise, but something to remember and be aware of when choosing to use a reference station network solution or set up a base on a local site control point or nearby monument and run off of that. I like to bring up the following personal example when discussing RTK in less than ideal situations. A few years back, I was asked to set a few additional lot corners on a job we had posted a few months prior. It was in a wooded area, and there were a few gaps in the forest that one could have set some decently reliable RTK points to start traversing from. But that was not initially done here. I got to site, set up a base, and started checking into property corners, and my checks were all over the place. A few were a tenth of a foot out or so in the open areas, and getting significantly worse as the vegetation closed in. One pin in particular that caught me off guard was over 4 feet out. The guard stake was still in place, and it was obvious it hadn't been tampered with. I set up a baseline and check shot via RTK and traversed in, and sure enough, I was seeing more or less the same deviation. When I got back to the office, I checked the job file from the data collector, and it was showing more or less acceptable RMS values. I bring this up as a warning. RTK cannot be emphatically trusted, especially in poor conditions. Did the original surveyor follow proper procedure? Well, if he went back at the end of the day and took a check shot, this blunder would have shown up. It probably would have shown up if he dumped his satellites between setting it and immediately checking it too. Was he right to use RTK in these conditions in the first place? That's a more difficult question to answer. There are some bush jobs where it just isn't realistic to traverse into each corner that's treed in. In the years I spent working in the British Columbian Rockies, hiking/rock climbing miles into a property corner where there weren't nearby openings in the trees that would allow you to set a baseline and traverse into, and even then, in those conditions, by the time you got to the corner, your accuracy probably wouldn't be much better, not to mention your client would have to absorb a very significant increase to the bill. The decision of when to use and not use RTK is a balancing act that each surveyor needs to make for themselves. At the end of the day, it's our job to act in the best interest of the public. Does it make sense to 5x our cost of a subdivision out in the middle of the bush to gain a few centimeters of accuracy? Maybe not. Does it make sense to set a baseline for you to set up a total station on to set a property corner that's 15 feet inside of the tree line in an urban area? Well, let's just say you wouldn't have to twist my arm too much to convince me of that. I tried to keep this video to a digestible length. There's a lot more to this story than what I touched on here today. The size of the data sets aren't nearly large enough to draw concrete conclusions from, but hopefully there's enough data to get you thinking and maybe running your own testing. In future videos, I plan to make a comparison between low, medium, and high-end receivers in varying conditions. I will explore best practices for running static networks and how static accuracy compares to RTK, and also how to incorporate both RTK and static observations with total station and leveling data in the same job via microsurvey StarNet to create a top-tier geo-referenced control network. I will add a link in the description to the datasheet for you to download and do your own analysis on if you so choose. Feel free to give your thoughts and opinions in the comments. And as always, subscribe if you want, like if you feel it's warranted, and I'll see you next time.